Welcome everyone. I think we had a good discussion earlier where we put the data into HOMER, and then we now have to see how we can simulate the data. Before going for simulation, we have another small areas where we have to input the data, which is on the resource section. If you see, this is resource. And the resource section, you have multiple areas like solar resource, diesel, economic, system control, emission, and constraints. Mainly, we'll look at three areas. One is solar resource, second is diesel, and third is economics. These are the three areas that mainly you have to look at. The other two areas, you can probably, you don't have to look at because it doesn't have much sort of connection to telecom activities. Solar resource. Now, as I said earlier, if you can put your site location and the time zone and hit the button called Get Data via Internet, it automatically gets the solar radiance data. And this is connected with the NASA database, and it works very well. There's no issue of that. So we have to get a reference sort of location data. Can we get a frequenting? Great. Can we get a example site location maybe in Uganda? A random latitude, longitude of any site. No, I mean, I'm not very literate about the location here. Which latitude and longitude zone over here?
It's the most closest place to the equator. 00.04.
Okay, so latitude 0 degree, and let's say 5 longitude.
You drive not far away into the equator.
It's very close, yeah.
Stephen?
East.
Any suggestion?
No.
Yeah, tell.
You should know this by now.
No? Okay, I can check quickly from my Google Earth. Where's my Google Earth? Down. Farther down. There you go. There you go. Taking time to load. I want to hit on the African region. Come on, there you go. So we are in.
Yeah.
There you go. There you go.
Choose an island site. Something on a lake.
Okay, we'll put something here, like this one, this place. Okay, so this is east.
Latitude between 4.
It's 1 degree 16 minute, and then 32 degree 14 minute. 1 degree 16 32. 1 degree 16 minute, and then 32 degree. What was that? Maybe 10.
Yeah.
Just take a random one. Yeah. Okay. And this is north and east. It's northeast. Yes, north and east. And then this is important one. Time zone. So we have to pick the right time zone. So this is GMT +3. East Africa. Okay. So hit the button. Get data via internet. I hope my internet is connected. I hope it will get data. If my internet is connected, it will get the data automatically. If not, then forget it.
And this goes where to get that data? This goes.
There you go.
It's going to NASA?
Yes, so the NASA database is connected with the NASA database, so it will pull the data from the NASA database. So we got a good sort of data on the radiation. So we got good average, 5.6, which is good one. So we have a steady radiation. What I see, the solar radiation is quite steady. I know this month, May, June, July, have a little bit lower, but average is quite good. This is good. Okay, so hit the button OK. It's already captured.
Where else can I say to save the file?
Oh, okay. I'll save the file.
Sometimes it
Hangs? Yeah. Okay. I'll save it. Training. Okay. Then go to the next bit, which is diesel. Now, this is the diesel cost per liter, and it should be the landed cost. So I believe it's about, what is the average landed cost of diesel? $1.30. $1.30?
Yeah, 1.3.
Let's take conservative value of $1.30. Okay. Done. One thing I forgot to show you, it's in the diesel side. Just in a 30 seconds. Now in the diesel side, when we did this configuration, we did it only in the cost tab. There's another few tabs: fuel, schedule, and emission. This can be emission tab, you can ignore, but fuel and schedule tab can be really utilized. Now fuel tab is essentially for, let's consider you're not using a diesel genset, rather it's another sort of genset like CNG, LPG based genset. What you can do is you can simply change the fuel and change the fuel curve. That's it. Okay, and there are multiple fuels, say ethanol, gasoline, methanol, natural gas, propane, biogas. You have multiple sources here actually. You can do that, and schedule is important, especially if the site is grid connected, or if the grid is available intermediately, or let's consider the site is located at the urban area, and by regulatory requirement you can run the site during night. So you can actually, in this tab, schedule tab, you can force off the diesel genset and force on the diesel genset if you want to, or you can optimize the diesel genset uses. That means, let's say, if you are not permitted to operate your diesel genset at night from, let's say, 10 or 11 p.m. till 5 in the morning. So this 6 hours, you can force off diesel genset and let HOMER to identify a solution or dimension which still can operate the site without having the diesel genset running the 6 hours. Okay, we can actually do that, but we're not doing that exercise here in this example. We can do it later on. Okay, just wanted to show it. Cancel. Okay, so we have done with the solar resources, diesel, and the last bit is economics. So economics, what we do is we take the interest rate, we take the project lifetime, we take the capital cost, fixed capital cost. Remember, we haven't taken the cost for the solar PV accessories. We haven't taken the cost for the rectifier cabinet. We haven't taken the cost for the PV installation, the civil works, and we also haven't taken the cost for controller. If you have any control system in place, let's say intelligent controller, if you want to have. These are not considered here. So what you can do is you can add up all the values and put it as a fixed capital cost here. Or you still can keep it 0, and then in the last of today's session, we'll show you an Excel business case. You can place all the value at the Excel business case and automatically calculates. So either way, it's possible. So we can go either way. So I would prefer to put it here, not in the Excel sheet. Okay. So I will start with interest rate, maybe 16%. Maybe the project lifetime is 10 years. Fixed capital cost, let's consider another $10,000. This is what I was referring to.
Civil works and
it's just a random value. Yes, civil works, the accessories cost, like the mounting kit, the cable, the grounding, so on and so forth. Yeah. The fixed O&M cost per year. Now, remember, we haven't taken the O&M cost for individual component like battery, PVs, rectifier. We haven't taken any individual O&M cost. We put a 0 while do the configuration. But we have taken a O&M cost only for the DG. DG diesel genset of $0.50 per run hour. So we have to take all the O&M costs of other equipments. Let's consider as a package cost. Let's consider that you have a partner who actually will be responsible for doing the O&M activities of this particular power generation or power management system, and you give a package deal to them. Let's consider the package deal is about $2,000 per year, $2,000 per year, maybe.
yeah, it's roughly $150.
Yeah.
Per site visit?
No. Yeah, per month.
Per month. So it eventually it's $2,000 or $2,500. Let's consider $2,000. Okay. So this capacity shortage is not for you. So this is interesting topic actually. The capacity shortage penalty. This is for the grid power generators. Now, if your site is connected to the grid, and if you're an ESCO generating power for your partner or your client, and you could not able to meet the capacity requirement, annual capacity requirement, or monthly or daily capacity requirement. So based on not meeting the requirement, you may have a penalty clause imposed. So if you want to convert that data into a business case, maybe you can bring it here. But for you, no, it's not actually necessary to put. Okay. Okay, so we are done with configuration.
Is there nothing in there then that describes the distance from the load to the PV to calculate his cable thickness, cable length, that sort of thing?
You took an efficiency ratio, though.
So I need to know if I use a 35 mil or a 50 mil or a
Good question. Good question. No, so this is not considered here. Now, the efficiency thing, the power generation, what has been generated at your PV, HOMER is considering that your site is nearly located, your consumption location is nearly located, the load is nearly located, and it's actually not considering any sort of loss there. So I think this is a very good point, and you have to probably, you have to take that manually and see how we can adjust this. So you have to hit the calculate button, hit the calculate, you get a 3,150 simulation.
So we're going to go through all the options.
No. No. Let's see what comes up with. Still calculating. Is my laptop slow or? There you go. Good. Okay. Now, there's two tabs here: sensitive result, optimization result. Okay. And in optimization result, there's two tabs. There's 2 points: categorized and overall. If you click the overall button, you see the whole list of results. In categorize, is only picking some of the core outcomes. And it's calculated based on multiple selection criteria that HOMER has in place, like cost of power generation, CAPEX, OPEX, and dimension. These are the 4 areas that HOMER usually calculates. And these are the categorized solution. Now, if you look at the sensitive result part, you see there's only one result showing here. And HOMER thinks this is the best result. HOMER thinks this is the best solution for this particular site. And this is based on cost of energy per kilowatt generation. And saying, it's suggesting that the cost of power generation for this particular site of the data that we input is $1.2 per kilowatt. Okay, so it's based on the data that we input. Okay, so this is not a real figure. Now, what we can do is we can look at the optimized result, sensitive results, or we can look at the overall and see and do some comparison. Now, what are the few things that you have to look at before selecting a site? One of the key things is definitely the cost of power generation per kilowatt, number one. Number two, the CAPEX, where you are putting more CAPEX or less CAPEX. Number three, what is your strategy? Do you want to reduce your DC run hours up to what level? In many operators, they have a strategy of using the diesel genset for about 3 hours average per day. So if you have a strategy of using a diesel genset for three hours per day, which is about 1,000 run hours per month, then you come up with a sort of different approach. And then the fourth element is the operational cost, the overall operational cost, which one is showing lower. So these are the 4 areas that you have to look at while selecting the sites or selecting the solutions from here. And then once you double click, I will show you another 2 criteria to look at while selecting the right solution. So another area that is a logistics related area, not technical, which is the land availability. Now, 6 kilowatt, HOMER is suggesting 6 kilowatt is the best solution. But is it going to be the best solution if you don't have a land? No. So for 6 kilowatt, you have to have, let's say, about 24 pieces of PVs. So 24 pieces of PVs will need about 35 to 40 square meters of land. Do you have enough land available or not? Do you have any land without having shading? So these are the things that you have to look at practically. Now, if you think that this is not possible, but you only can go up to 4 kilowatt, so 4 sets of PV installation, then you have to look at 4, which are the options for 4, and even in 4 kilowatt, there are multiple options given. Now, what we'll do today is only look at 6 kilowatt, which have been suggested by HOMER. sensitive result selection.
If you are aware of your land limitation, can you already, when you set up your PV panel during the initial phases, limit it to 4,000?
You can't do that. You can't do that, yes. Okay, so what we'll do is, so what is this suggestion? This suggestion is saying 4 kilowatt PV, 8 kilowatt, that means one piece of diesel sensor, which is 8 kilowatt. It's suggesting 24 pieces battery, that means one string of battery bank of 600 ampere, 6 kilowatt of converter, that means rectifier, and suggesting the initial capacity is $39,000. And your operating cost per year is $2,250. And net present cost, NPC, is about $50,000. Cost of power generation per kilowatt is $1.2. And look at this, renewable fraction, 0.87, means 87% power will be generated by the green solutions. That means by the PV. And rest 17%, 13% actually, will be coming from genset. Now, if you just look at the overall result and see, just look at this. So this solution has a renewable fraction of 80%. This solution 83%, 77%, 74%, 71%.
Again, the renewable fraction.
Renewable fraction is the contribution of power. So let's say from the source, generating source.
So that means that 71% would be coming from the
PVs, right? And the rest will be coming from the genset.
So if we remove the genset from this,
yes,
we'd recalculate again, and then
yes, it gives you. Then it will give you either it will tell you whether the PV is enough or not, and if the PV is enough, then it will give you some solutions. If it is not enough, then it will suggest you can you add another power generation source or expand the PV footprint. This is what they will suggest. You want to see it? We can do it right away.
Yeah, I think it'd be good because it's a trade-off against the diesel genset.
What you do is just click add remove button, take out this GC. That's it. Okay, and do the calculate again. Let's see what it suggests. You see, it's saying that HOMER found no feasible solution because of the maximum annual capacity shortage constraint. That means you shouldn't be having any capacity shortage. That means it has to create the power what is required. It has to generate the power what is required. And it's a problem that HOMER identified and is suggesting, number one, consider a larger PV array. Number two, add a generator. Number three, consider a larger battery bank. Number four, increase the maximum annual capacity shortage. Maximum annual capacity shortage means that if you're an ESCO, you can go up to a contract with your partner of capacity shortage. That means, let's say your capacity requirement or load requirement throughout the year is 10,000 kilowatt hour, but you have a contract with 50% shortage capacity. That means you can go up to 5,000 kilowatt hour generation. Doesn't really fall under your category for telecom. It goes for the ESCO category, so eventually forget about it. So it's actually suggesting that either go for larger PV or add a genset. So either way you can solve this problem. Now we'll go back, add this genset. It's already been configured, so you do not probably need to do anything. Yes, it's already configured. We have to calculate again.
Is the PV shown to go directly into the site load? Is it not going to the battery?
It's going to battery.
Yeah,
it's going
by
into the
the
DC
bus bar.
So yeah.
Okay. These batteries are cycling to a certain depth of discharge, I assume?
Yes, you'll see that. So the beauty of HOMER is you can actually go for hourly data. So there's a tab that I will show you right now after this. Is you can actually literally see throughout the year, every single day, what is your power generation from PV, state of battery charge, your power requirement that you've been drawn from the battery, your genset. You can actually see everything. You can focus everything.
I ask because it's one battery string really is what we have here, right? In practical terms, what we've seen with other ones is that if one cell and that one fails, the whole string goes down, and now your site's down. So I wonder about the redundancy.
Yeah.
So a lot of times we'll do two strings just because if one fails, you've got that backup.
Yeah. Yeah, and I think this is a very valid point. I guess this is all about strategy, that do you actually want to strategically create two set of battery having 400 ampere hour, or you want to have a two set of battery because you want to get a higher autonomy. So these are the strategy that you have to set. So we will go into that. So okay, so this is the solution that we want to discuss a little bit detail. So once you double click, where did it go? It is one. Okay. Okay. So this is after double clicking on the solution. You see this window where cost summary, cash flow, electrical, PV, DG, battery converter, emission, all the data. These are the things that you can see detail on. Now, I will start with electrical, except for cash flow. I'll come to cash flow later on. Electrical. See, the PV array is contributing 87%. Yearly basis, it will produce about 9,813 kilowatt. Based on this example, 87% of your required energy or required power for this particular site. And generator will be producing 13%. So look at this right-hand side, excess electricity. Now, the excess electricity is shown about 13.7%. This is another KPI that you have to always bear in mind. The excess electricity at the site should be less than 5%. That means if your excess electricity is more than 5% and if it is unutilized, it is actually not an efficient solution. Because you're having an excess electricity and it's getting wasted. This excess electricity is, why it is excess? Either it's because you don't have enough load to consume this power, or you don't have enough storage to store this power, excess power. So having more than 5% excess electricity is either you have to reduce your PV string, either you have to increase your battery, or either you have to increase your load. So considering all of these facts, it's always good to pick a solution where you have an excess electricity less than 5%. How you do that? So if you want to optimize that, so the best thing is increase the battery capacity. But before going for increasing the battery capacity, we have to see what is the battery autonomy that's currently shown in this solution. So let's do that. Always bear in mind excess electricity less than 5%.
But doesn't that assume that the battery is 100% for the life cycle of the... there's some degradation of the battery over time. So won't that percentage over the years...
This is an average percentage through the business case that you have collected.
Okay,
so this is the 10 years. Exactly.
The life,
yes. Right. So.
The battery over time.
Right.
The losses you described, would they be factored into this here? So we have actually less excess electricity because of those losses.
Yeah, I don't know what losses are put. I mean, is this? Yeah. We don't know what.
Very good point. Very good point. So. Once you add those losses, let's say the cable loss, the transmission loss from your PV station to your, the BTS site, maybe you have to consider that the excess electricity would be a little bit lower than that. But in most cases, as a standard sort of installation, what we see here, in most of the cases, PV installations, from the PV panels at the junction to your bus bar. Maybe the distance is about 10 meters, 15 meters. I guess if you go for 35, is it the 35 is the standard one?
35, no.
Yeah, 35 is the standard one. I mean,
over 10, it's probably to 50 mil.
Yeah, it's over 10 is 50. Yes. It's within a 10-meter distance, about 35. Yeah, this is something that's standard. When we think that it's working fine. Anyway, so let's move on. So PV tab talks about your PV rated capacity, what sort of PV output that came from this solution. Capacity factor is 18.7% that we see from here. We will jump onto the DG. DG, interesting, look at that, hours of operation. So DG actually will work about only 233 or 250 hours per year, which is about 1 hour average per day. Now, don't take it the average, because in many things, once we'll go for the hourly data track, you will realize that the DGL genset will not be kicked off in many of the days. And some of the days it will be kicking off and it will be running in a very high rate for a few hours and charge the battery entirely, and then wait for the battery drain to a very deep level. I mean, whatever level we set during selecting the batteries. It all depends on what we selected. So you can't blame HOMER or you can blame me. It's all about how you're inputting the data of battery. Now, how many numbers of start? 58. That means it's average every 5-6 days. It's starting for once. What is it suggesting? Okay. I think these are the whole fuel consumption. Look at the right-hand side corner. Fuel consumption, 506 liter. This is what the fuel will be consumed by the diesel genset in this particular solution per year.
The diesel will have gone off by the time that's used out of the tank.
Could be stolen.
No, yeah. So one of the things that we discussed quite detailed today, one of the core component, especially for site maintenance point of view, is what we see as a common practice in Africa is people are bringing a lot of fuel in one go and not going to site in 2 weeks, and then again bringing a few hundred liters of fuel again. What we see from some of the places where the diesel theft is quite significant, like in India, Indonesia, in Pakistan, what they have started doing is they started going to the site infrequently and putting in less fuel instead of bringing more fuels in one go. So they're going to the site in every, let's say, 3 or 4 days, every 4 days, and bringing based on the power, based on the fuel required, based on the previous experience, they're bringing less fuel. And that's one of the way they can closely monitor the fuel consumption and reduce the theft of the fuel. And
Spend all the fuel in the traveling.
no, they're not going for one site, right? They're going for multiple sites in one go. So and no. You now this is actually, you know, this is how you think of. This is actually wrong thinking. Right thinking is it one single car will be delivering to one single site, or it's a third party who is actually responsible, maybe not only for ATC or not only for MTN, maybe for other solution, other partners there. So they actually, you know, it's a package deal for them. So it's a package. The way it's successfully implemented in some of these places in Asia is if the price of fuel is, let's say, $1.10, they're saying, well, I'll pay you $1.12, and you manage however way we want to manage it. And that's how the whole thing actually is operating on the ground. And those guys are becoming smarter, I mean the fuel delivery guys, and they are taking more contracts with multiple tower companies, multiple mobile operators in the same vicinity. And it's not a nationwide contract, it's a local contract. Like for one division or one district or one province, there's 1 or 2 suppliers. And it's actually clustered, you know, you have like 4 or 5 clusters, and you have about like 200 sites in those 4 or 5 clusters. They go for delivery one go delivery, all like 20, 50, 30, 50, 60 sites, come back. So it's actually an efficient way of utilizing the fuel, the delivery cost. I think this is something that we have to explore, whether it's possible to do it here or not. If it is possible, then definitely that's a good way. Otherwise, you know, probably we have to delete it. I mean, sending 500 liters of diesel, and you never know what's going to happen on the ground.
Already reducing the amount of diesel they deliver to the site.
I think, yeah.
Increasing the fuel.
Yeah, and I think this diesel thing, I mean, diesel availability is quite, and even if you go for the deep rural areas, you have the diesel depot there. So I think you don't have to deliver from a long distance if you can create a local partnership. But again, creating a local partnership is always very challenging in the sense that how trustworthy those guys are, how efficiently you can manage this partnership. So these are the technical, I mean, these are the pure operational issues. Okay, going back to the other discussion, let's look at the battery tab. Okay. Autonomy, which is the middle of the autonomy, 20.2 hours. This is one of the most important elements here. So how many hours of battery autonomy you need to have? Now, I'll come back to the point that you raised a few minutes ago, is having 2 string of battery to have redundancy. And the same point is connected with autonomy. So if you can have another bunch of batteries, let's say this is 600 Ah battery here. If you have another 600 Ah battery, it ultimately increases autonomy of the site, 40 hours to maybe 20 hours to maybe 40 hours or 42 hours. But at the same time, it gives you redundancy, but that also increases your capital expenditure. So the way you can do it is you can try to make it 300 H or 400 H, make it 2 string of 400 H, and see what is the outcome looks like. Maybe it can be a more efficient way, but yeah, you have to try it. Okay, I'll jump on to emission. It gives you a very good idea of what sort of carbon dioxide emission will be happening at this site. Especially considering the fact that the diesel genset will be working for about 250 hours per year. Considering that, what will be the carbon dioxide emission, carbon monoxide emission, all this emission will be shown here. All the data, this is very interesting, you'll love it. So, plot. So, there are multiple variables here, starting from global solar, incident solar, DC power, DC primary load, PV power, generator, excess power, then battery startup, state of charge in the bottom side, battery energy cost. So all these things are different variables. You can see it from here. Let's consider a couple of elements. One is primary load, PV power, battery state of charge. Okay, let's take only these three areas. Let's see what is the power requirement and then how the power is generating from PV or DG, and then what is the state of charge of the battery, and see how we can correlate. So we have power load. Okay, we can exclude this. PV power, generator power, and battery state of charge. So if you see from here, 1st Jan to 7th Jan, you can literally see the entire year from Jan to December. Or if you want to go have a closer look, you can actually do that same. You want to see here, you can see it. So this is 3rd Jan. And what is happening, the black line which is going up and flat and then completely gone down, this is actually a genset situation. So the diesel genset is kicking off, it's about 2 in
the morning.
Yeah.
what's the time this? 2 a.m. Yes, the genset is kicking off in the morning, and it's running on a very high load, about 6 kilowatt, and then continuing for a few hours, and then it's going down again at like about 7 a.m. Right, and your battery state of charge is changing here. Once you kicked on your diesel genset, battery start charging, and then in 7 or maybe 8 a.m. when the PV started generating power, the diesel genset is off. You still have a good battery state of charge, battery is discharging, and at the same time the PV is providing power to BTS, and maybe it's charging a little bit. Once it started picking up, it's also charging the battery. You see the battery curve is going up. So literally you can actually see the state of charge of the battery versus your PV power generation and the DC power generation. And you can see the next day, you can go to the next day, next week, you can see it from here. So the battery is not kicking off every day. You see there's no battery, sorry, there's no DG kicking off here. No DG. Here, DG is here. Again, no. Yes, here. So this is a good way of forecasting which at the time the diesel genset will be utilized, which at the time it will not be utilized. Now, I think this is one of the good way of forecasting the overall situation. I mean, HOMER gives you a very, very good close proximity sort of forecasting of your solution. And we know from different sources, that this tool has been utilized by different global mobile operator groups, different ESCOs, who have used HOMER and deployed hundreds and thousands of sites. We have clear sort of examples in place who have utilized HOMER, and they have given us a reference that the forecasting that HOMER did is actually completely matching with their current performance of the site, and they've been operating in the last 1.5 year or 2 years time. So this is a good way of looking at the overall site situation. Then I will go back to cash flow, which we haven't really discussed. So the cash flow, if you look at the cash flow tab and go for details, it gives you a cash flow of the site. So we will go for nominal cash flow. So all the items are here, and it's from year 0 to year 10. So you actually see a complete sort of year-on-year cash flow. That includes the CapEx, OpEx, and overall cost that you have considered during planning the equipments. So this is one of the good way of also bringing the technical solution plus your financial cash flow through this HOMER dimensioning. So what we do usually is we can copy all this cash flow information and paste it in an Excel sheet to create a good business case, like comparable business case. Or what you can do is you can just click on this report, XML report. It can generate XML or HTML reports. The overall solution can be generated in one HTML based or XML based report, which is quite nice and presentable. But that does not give you the return of investment, NPV related scenarios, because in order to get a return of investment or net present value, you have to have a comparable element, and you have to compare with the existing diesel cost. Now, if you don't have an existing diesel, there's no way we can put the existing diesel cost here. So to create those financial indicators, what we do is we copy all this data and paste it in an Excel sheet. So in the next few minutes, we will walk you through it